Gord, you got it? All right. Let's begin with a word of prayer. Dearly Father, we thank you for this day. Again, Lord, I thank you for these students. Pray be with us. Help us to, again, Lord, glorify you. What we do, just to understand a little bit more about your law, Lord, and how you make creation work, Lord. In your name I pray. Amen. Okay, so one of you mentioned that you had a question about math or something. Do you still have a question? Or?
No, I figured it out.
Figured it out, okay.
Yep.
All right. Well, in that case, I will go on to talk more about the inclined plane problem. So here we'll suppose that the force due to friction is equal to mu sub k times the normal force. I'm going to assume that it's moving. I guess that's, well, let's think about that as we go on here. And let's put consider mass m on an inclined plane. Now I suppose I could consider the situation, and I've asked this question before, and it's an interesting question. Maybe I should ask it again. Suppose you have static and kinetic friction, right? Then you can ask the question: does the box slide or does it not slide, right? So fine, let's even do that. I'll just. All right, so here's a picture of what's going on. All right, so the angle of inclination is down here. This is what we call theta, usually. Theta's angle of inclination. And then we look at some mass m up here, all right? And then what we're going to do is we're going to study the forces on this box and try to come to an understanding of its equations of motion. That's governed by Newton's laws, all right? So what's at play here, really? You got, let's see here. I'm going to draw them right here for artistical reasons. So I've got mg, which I'll draw this way. And I think it'd be convenient if I just connect it with the bottom line there. That's just for my own convenience. mg is like that, right? Straight down. And what other forces are at work here? What's that? Yeah, the normal force, right? So there's this one, the normal force. These are not necessarily to scale, by the way. Normal force goes like that, and the force of friction is which direction's that? Yeah, I guess it's kind of a loaded question. You're like, well, that kind of depends on what's happening. If the box is at rest, the force of friction is certainly up the plane, right? But if the box is sliding up the plane, right, the force of friction is down the plane. So the question, which direction is the force of friction, really depends on the motion. If we're considering the case of static equilibrium, all right, which is a good place to start, then certainly the force of friction is up the plane, right? So let's start with that. Let's assume it's a static situation to start with. All right. Anything else? I mean, you could add another force, right? You could put some little dude right here and have him push on the box, and that'd be a different problem, right? Sometimes I look at that one. But let's start with this. Okay, so there's really two directions. There's the direction which is parallel to the plane, and there's a direction which is perpendicular to the plane. And so that's my terminology. I mean, some people use x and y with a different meaning here, but I don't do that. I'll just say that this gravity force can be broken into two pieces. I can decompose mg into the perpendicular part, right, and this parallel part. And let's see here, this is going to be what? Now if you look at the geometry here, if this is theta, the angle up here, let me call it here, beta. Well, beta and theta are complementary, right? So in other words, beta is 90 degrees minus theta, But on the other hand, that forces theta to be over here, right? Do you agree? I hope you agree. It is in fact true. Okay, so theta is now once you realize that this angle in here, this interior angle is theta. Yes, sir.
Should we really call that theta since we already had another theta there?
I mean, it's the same theta. Yes, that's my point. But I appreciate your concern. Let's see here. That is a funny question. Let's see here. So theta is again here. My point is then, well, if you look at this as a right triangle, right? That's the whole point, parallel and perpendicular. These are orthogonal directions. And so what I have is I've got mg cosine theta here, right? And then this guy down here is mg sine theta. Again, this is perpendicular and this is parallel to the plane. All right? It's important you understand this. That's why I'm slowing down a little bit. All right. So then we can apply Newton's laws, right? And so let's drop the assumption that it's static. Well, no, I don't want to do that. Well, sorry. Let me think for a second here. This won't change. I can cross this out, right? And say, suppose what? Sliding down plane, right? With that assumption, same picture, right? Okay. I mean, of course, I face the Goldilocks problem again. Like, is the force of gravity enough to overcome the maximum force of static friction? You know, so let's just suppose that it is. All right. So it would slide down the plane. Okay. Anyway, so once that's clear, let's say that acceleration is equal to the let's say a is equal to the acceleration parallel to the plane, right? And so I got two equations of motion, right? On the one hand, I've got Newton's laws. I have the mass times the acceleration, and so here I'm talking about the parallel direction. And if I said parallel to the plane, I have two choices, right? I can either make acceleration positive down the plane or positive up the plane. I don't have a convention, really. You could go either way. What do you want to do? What's that? Positive down the plane? All right, great. Then if I do that, what do I have? I have minus the force of friction, right? That's going up the plane. It's in the parallel direction. And then what? Yeah, plus mg sine theta. Not cosine theta. As I was just talking about over here, the cosine theta is the perpendicular part of gravity. Sine theta is the parallel part of gravity. In other words, it's not the angle you're looking for. All right. You're thinking theta in terms of, anyway. You have to look at the picture and work it out. All right. Perpendicular direction. Well, here, what's the acceleration perpendicular to the plane? It better be 0 if the box is on the plane, right? Otherwise, we'd be either accelerating into the plane or off the plane, either of which would be pretty strange, unless it's a rocket box or something, right? But we didn't do that. So 0 is equal to what? And I will take this direction as positive, so that makes the normal positive. And then what? mg cosine theta, right? So check it out. this tells me that n, the normal force, is mg cosine theta. Yet again, as I was advertising to you last time, you can't just assume the normal force is mg. That's not always true. This is another case where it is not true that the normal force is mg, unless this is a really stupid inclined plane, the flat one. Put theta equal to 0, it's mg. Otherwise, no. Okay, so then, once you know that, you can go back up in here, but the force due to friction is mu times n, which in this case is mu mg cosine theta. Right? And so what do I have? I've got ma is equal to minus mu mg cosine theta plus mg sine theta. And so there we have it. We have ma, or acceleration a, is equal to, we got here, g times sine theta minus mu cosine theta. There's the acceleration. Yes, sir?
What does mu stand for?
The coefficient of static friction, well, coefficient of, I guess not static here, it's coefficient of friction. But the analysis I'm doing here, you could either go with kinetic or static, right? If you think about it. Well, kinetic, assuming it's sliding down the plane. Kinetic up the plane is a different story, right? Kinetic up the plane means there's something else involved, right? Somebody gave the box a shove up the plane and it gave it some velocity upwards. And that would be a different problem, because friction would go the opposite direction. So now, all right, so suppose the box is not moving to start with, all right? Suppose it starts at rest. We can do this analysis, right? And we can ask the question, does it stay at rest, right? When will it, if it starts at rest and we let it go on a given inclined plane with a given coefficient of static friction, how do we know, given this analysis here, if it would slip or stay put? Yeah?
You have to look at your force equals mass times acceleration formula and see if like the force of gravity on the box normal to the plane or parallel to the plane is greater than the force of friction on the box.
Greater than the possible force of friction. But yeah, that's what you could do that, right? But we already did this, right? So the question really boils down to, that's what we just did. The question here, that's what this is. This is the force of friction, right? This is the force of gravity, and the question is which one of them wins. Now, in the static case, right, this is the maximum possible friction force that you can get in the static case, right? Is when we put mu equal to mu sub s, right? Max static friction. So to answer the question, really, we would have to, give either a theta or a value of mu and then ask the question, right? So let's suppose that mu static is equal to 1. That's pretty ridiculous, all right? That's very, very sticky. So suppose the coefficient of static friction was 1, then what would you have? You would want to see, can I solve 0 is equal to, g times sine theta minus cosine theta. Can you solve this, for a reasonable angle? Is there an angle of inclination which does this? That would be the maximum angle. That's right before you go over the edge. What's the solution to that? Well, divide by g. You got sine equal to cosine, which is what? Right, theta equals to 45 degrees. So if you had an inclined plane with a coefficient of static friction of 1, you can go all the way up to 45 degrees. If you get past that, then you don't have enough friction force to keep gravity from winning, and it'll start sliding down. However, if the coefficient of static friction was less than 1, then the angle would be smaller, right? By the way, any angle smaller than 45 degrees, you still get what? You still have enough mu cosine theta. You have enough of this to oppose that. Remember, the coefficient of static friction force is a variable force, so it'll just match g sine theta, whatever it is. So So anyway, I mean, stop talking about this. I think I've shown you enough that you could answer questions. But I don't want to try to answer all possible questions in this example. I just want to show you enough that you can get started. Now, what the gentleman said about looking at the balancing of the forces is like equivalent to what we're doing, right? But I hope you realize the clarity of thought that comes from applying Newton's laws. Because balancing forces, seeing intuitively which forces have to be balanced and how they balance, it's a dangerous game. And it tends to ignore the fact that there's this MA term here, right? A lot of people have pretty good intuition for the equilibrium case. But the accelerated case, very few people can just do with like balancing forces and stuff. I mean, that's what'll get you. All right, let me work another example here. Unless there's a question. Okay. So this is number 10, I think of 4. And the question is about some sort of accelerating of chickens and some kind of chicken gun. So apparently you have a chicken gun. I guess it's a chicken cannon. Not a gun. If you can shoot a chicken, it's not a gun anymore, right? Oh, for some reason we're shooting chickens at airplanes. Oh no, this is supposed to be to keep the... I'm not sure. Anyway, this is... I guess I don't need to make it... Oh, this is a one-dimensional problem, isn't it? Oh, that's no fun. Oh man. I guess we're just shooting it like that. Fine. So, you design a test gun that will accelerate chicken-sized objects so that their displacement along the gun barrel... So let's say that this is x equals to 0. And so I can't draw a chicken. I'll use this with a C in it to denote the chicken. There you go. So this is chicken. All right. And but the formula for the chicken's position is equal to 8 is equal to x is equal to rather 8 times 10 to the third, otherwise known as 8,000, t cubed. Oh, t squared. Minus, maybe I regret this, not using scientific notation here. That looks like a 50,000. T cubed. All right. And it apparently takes t equals to 0 to t equals to 0.03 seconds to fire the chicken. All right? This is given to us. And then they ask a variety of questions, all right? How long must the gun barrel be? What will the speed of the objects be as they leave the end of the barrel? What is the net force exerted on a 2.5 kilogram object at t equals 0 at t equals 30 seconds? We can answer all these questions. All right, so let's start with the easy thing. What's the speed? What's the speed of it as it leaves the barrel? Exactly. dx dt is 16,000 t minus 150,000 t squared. So the velocity at time 0.03, we just have to plug it into that formula, right? So 16,000 times 0.03 minus 150,000 times 0.03 squared. What does that give us? Any guesses? So what'd you guys get? All right, I'm getting impatient. I'm going to tell you 345 meters per second, give or take. For my numbers, approximately 345 meters per second. Do you guys get the same, roughly? Now, I said this was the easiest part. I'm a dummy. What's even easier? How about where is it at t? How long is the barrel? Well, that would be, given what we were told, x of 0.03, right? That would be, this is what's in up there here is given. This is number 10 of homework 4. So how long will the barrel be? Well, that's simple. I just have to check what is x of, what's the formula if I plug in 0.03, right? That should tell me where it is when it leaves the barrel, which is the length, right? So I've got 8,000 times 0.03 squared minus 50,000 times 0.03 cubed, which gives me about 5.85 meters. Wow, that is definitely not a gun. That is certainly a cannon, right? I mean, it's like one of those. You see those idiot daredevils who shoot themselves in cannons? You know, it's like one of those things. I'm sorry. Do you have a relative that works for the circus or something? Have I insulted you? I'm sorry. I should be more conscientious. I should make this a safer space for you. All right. Okay. Then the question is more interesting. What is the net force exerted on a 0.25 kilogram object? So this is part C. So we're saying the chicken is 2.50 kilograms. Is that a reasonable mass for a chicken? How much does a chicken weigh? I guess it depends on the kind of chicken, right? And the question, though, is what's the net force at t equal to 0 and also at t equal to 0.3 seconds? So there's two things here. Actually, this is part C and this is part D. T equals to 0. T equals to 0.03. So how do I figure that out? F is equal to what? F is equal to what? Mass times, the net force at least, is the mass times acceleration, right? We're given the position. We've got the velocity. Next, we get the acceleration. So the acceleration is a function of time, right, is what? It's 16,000 minus 300,000 t. And so all I have to do is to plug in time equal to 0 and time equals to 0.03 to find the acceleration at time 0. Acceleration times 0, that one I can do without a calculator, 16,000 meters per second squared. The acceleration at time 0.03, I will need the calculator for. That's in meters per second squared, right, given the units of everything here. All right. So I get 7,000 meters per second squared. I get 16,000 meters per second squared. That tells me the force at time, the net force at time equal to 0 is 16,000 times the mass, which is what, 2.5. So I get 40,000 newtons, otherwise known as 4.0 times 10 to the 4th newtons in ye old scientific notation. The net force at time 0.03 will then be 7,000 times 2.5, 17,500 newtons, aka 1.75 times 10 to the 4th rather, newtons. So there you go. All right, the bigger picture from this example is simply this, is you should understand once somebody tells you the position is a function of time, it's a straightforward matter of calculus to figure out the velocity and the acceleration, and if you know the mass, the net force which is responsible for this motion, all right? This is kind of a backwards problem, right? In the sense that we're starting with our end goal, like over here, we hadn't gotten to that level, but if I was to put some coordinates down, we could find the position as a function of time over here, right? Like, if I say that this is the x direction, right? Then I'd have x of t is 1/2 g sine theta minus mu cosine theta t squared, provided it started from rest. Right, so if you integrate that, you'll get the position as a function of time, like so, right? But we found that by first analyzing forces and then getting to that. In contrast, this problem, the position as a function of time falls from the sky, like so many web assigned problems. Much like the chicken. All right. Any questions? Okay. All right, let's do some more examples. These are homework 5 examples. I think you guys will like these more. Less calculus, more physics. There's a question? No? That's okay. I mean, I'm just asking. All right, here we go. Problem number 1. This is homework 5, number 1. I could try to be more clever and come up with examples that I haven't assigned you in homework, but my experience is that if I work with different numbers, it's still helpful for you guys to see these problems. So here's the deal. We've got two weights that are hung at opposite ends of a rope that pass over a light frictionless pulley. All right, and then the pulley is attached to a chain that goes to the ceiling. Here's the chain. All right. So here's the weights, and we're given the weights. Then the question is, what's the tension in the rope and what's the tension in the chain? Now I'm going to change the problem a little bit. In the problem, you have equal weights on both sides. I think it's more interesting if we make them unequal weights. I think it's actually more interesting if I give you some masses. Let's suppose that this is M1 is equal to 30 kilograms, and let's suppose M2 is what? 50. All right. Thank you. Indecision is one of my chief vices. Okay, so the question then is, find tension in left, right rope and also the top chain. And then also find the acceleration for system. And we're going to define the acceleration by a little picture right here. We're going to say that this is the positive direction. You'll appreciate that because you guys like accelerations to be positive. That's not required. I could just as well define the acceleration to be the other way, and then we get a negative number for the answer, right? Okay. All right, so here's what we do. It's always Newton's law. So what we do is we pick pick any one, this one right here, and I look at the free body diagram. So I've got M1G down, right? And I've got this tension, let's say T1 up. All right. And then over here, I've got what? I've got M2G down. And I've got what? T2 up. Do those tensions have to be equal? Each other? Let's see here. These two ropes, right, they pull on the pulley, and then that pulley does what? So, I mean, this much I know. The tension in the chain up here, tension in the chain will be the net mass that's hanging here, which is what? M1G plus M2G. That will be the net, that will be the tension in the chain. All right. So, there's something I'm forgetting. Well, let me go on here. It will hit me eventually. I don't think I've said anything wrong yet. Give me some time. All right, so M1A is equal to what? And M2A is equal to what? So given the direction we have here, right? That means T1 is positive, right? And what else? Minus M1G. And over here, let's see here. Now, gravity is in the positive direction. The tables have turned. M2G. And then minus T2. There's a reason these tensions have to be equal. If they weren't, that means there'd be a net force on the pulley, which means the pulley would be accelerating somewhere. But it's not, it's fixed in place. Right? So there's nowhere, I mean, there's nowhere else for the force to go. The tensions have to be equal, otherwise you'd have a net force on the pulley, which would contradict the fact that it's in equilibrium. There are other ways of looking at this, but basically, rope not slipping and pulley massless imply that T1 is equal to T2. In fact, those tensions have to be equal. So in view of that, feel better soon. This is the correct protocol. If you're feeling deathly ill, leave. This is correct. I'm not trying to get you guys to leave. I'm just saying. Well, if we all left. No. Sorry, I should behave. This isn't physics lab. I can behave better here. So what I'm saying basically is we can erase these. Now, you're like, wait a minute. Do you mean to tell me there's a case later in this course where the tensions won't be equal? Yes, I do. In fact, that case will come. It will come to us in due time. When the pulley has mass, when the pulley has a moment of inertia, then the tensions don't have to be equal, and you can end up with a torque on it. But there's nowhere for that to go at the moment because we're assuming the pulley's massless, so we have to assume the tensions are equal, which is super nice, right? Because then we can add these, and we get what? M1 plus M2A is equal to what? M2 minus M1G. And so this gives us the acceleration is M2 minus M1 over M1 plus M2 times G, and there you have it. Now the problem one, and I should really put a tilde on this because by now pretty much left your homework. Of course, we can put numbers in, right? For this one, it's what? It's 50 minus 30 over 80 times 9.8 meters per second squared. What do we get? Ah, 0.25. Yeah, 0.25. Ah, stop that. Stupid fingers, not working. Yeah, you said 2.45? Yes, sir.
Is M2G positive because the block is moving down?
M2G is positive not because the block is moving down. Not because of that at all. M2G is positive because we defined, with this picture right here, this to be the positive direction of A. I could turn the tables here. I could put a 50 here. I could put a 30 here. If the picture stays the same, M2G will still be going down. Will still be negative in that equation. I mean, positive in that equation. But we'll end up getting A is minus. Because the same derivation goes through, but you'd have 30 minus 50. So I'm sorry, this is an issue for me because you guys you have this tendency to want to make the variables look like what you think is going to happen, but this is not a necessary thing. Like we can have anyway, I shut up. Point has been made. There's a question? I thought there was a question. All right, I'm just imagining things. That's good. I mean, it's bad. It's bad. So the tension, what's the tension then? Pick whichever one you like. M1A plus M1G, which is what? So we got, what do we got? 30 kilograms times 2.45 meters per second squared plus sorry, brain stopped working for a second there. 30 kilograms times, oh yeah, 9.8 meters per second. Still 9.8 meters per second squared. You know, gravity's so boring. It's always the same. You know, I teach this course every year, and the G is always 9.8. I really want to change it to 10, but you guys always reject that at the start for some reason. If you'd accept it, it would make our calculations that much easier. But no. Physically reasonable. You guys and your physical reasonableness. So annoying.
If we accept 10 on the board, will you accept 10 on the test?
Sure.
Yeah.
Yeah, you can. However, we all have to accept it because I don't want to grade two sets of answers.
Last vote.
Class vote. Who's in favor of changing G to 10 meters per second squared? We do not have Matthew, right? Yes, I do not have the power to change Webber sign now. Not within my power. There was once a time it was within my power. As a student at NC State, as an undergraduate, I was asked, I could have coded WebAssign questions. And there, I could have made my mark. I could have coded 10 meters per second squared into the WebAssign questions, but I lost my chance. I'd probably be filthy rich at this point if I just stuck with WebAssign. That's okay. I'm not in it for the money, obviously. But anyway. Yeah.
So the tension equation here, M1A plus M1G?
That I solved this one for T.
No, at the bottom in red. The very last thing that you just wrote. The initial equation before you started plugging in numbers. T
Yeah.
equaling M1A plus M1G.
Yeah.
Why are they both M1?
Because M1 is in this equation here. Because it's the Newton's law on the first mass.
Is that what you wanted to just... you could use either one.
Should be, oh yes, it should be, oh my goodness, take off 30% of my credit here. Newton's, yes. Oh man. Old Isaac there, he's going to be upset. We didn't give him his credit where credit was due. It's like, hey, it's my unit. Show some respect. Let's see here. All right. Let me look at this number 2. Actually, let me see what time it is.
Is that the tension of the rope or the chain?
Tension of the rope. What's the tension of the chain? It's up here. You have to put in the numbers, so it's bigger. All right. Let's see here. Certain streets in San Francisco make an angle of 19 degrees with the horizontal. That's a very bad 19 degrees, but you can deal. What force parallel to the street surface is required to keep a loaded car of mass 1,100 kilograms from rolling down such a street? So, what did they not tell us here, and what should we assume? All right, so they didn't tell us friction. We can assume there's no friction, all right? Which is somewhat troubling for the man who's trying to put the force on the block, right? So let's assume that we have, I don't know, he's got these big feet, and we've nailed his feet to the ground. So there we go. It makes sense. It's kind of painful. Oh, well. So, not slipping, right? So this is an equilibrium. An equilibrium means what? In other words, the acceleration perpendicular is equal to the acceleration parallel. It's 0. We always have acceleration perpendicular 0 if it's on the plane. But now we even have the parallel acceleration 0. Okay, so same song and dance as we just did a minute ago in the other picture. So I can look here. I've got, I've got mg down like this, right? And that goes into 2 pieces. The one piece is like this, which is mg cosine of 19 degrees. And then also we have this one, which is mg sine 19 degrees. These 2 purple vectors make up the actual gravity. And so what we have to have is we have to have mg sine of 19 degrees, minus the force. That has to be equal to 0, right? This is ma. All right? You're like, why do you have to think about ma equal to 0? I know the forces balance. It's intuitive. Great. You're right. You have a good intuition. But you should realize it's coming because we're in equilibrium, the acceleration 0, and this is Newton's second law. That's what you're using. That's what guiding your intuition is Newton's second law. So there you have it. F is equal to mg sine of 19 degrees. And, of course, that's 1,100 times 9.8 times the sine of 19 degrees. What do we get? Newtons. How many? If I believe the WebAssign answer key that I'm holding in my hand here, we get about 3,500 newtons. I got 3,510 newtons, give or take. Excuse me. Blah. Sorry. Let's see here. To give you a sense of that, maybe we weigh, I don't know, some of us might weigh like Probably nobody weighs much more than about 100 kilograms here. 100 kilograms gives you what's your weight? If your weight's 100 kilograms, what's your excuse me, if your mass is 100 kilograms, what's your weight? If your mass is 100 kilograms, what's your weight? What's that? Ah. I'm going to bring duct tape in here. And we're going to get some poster board and just duct tape over it. That's what I'm going to do. Oh, just get some of that like spray foam and just like fill it up. You know? Oh, this is being recorded. Now they'll have evidence. They'll know who did it. No, it's not the kind of vandalism which is appreciated. My brother works with a professor, and there's these vandals that broke in to his office on the weekend, and they ripped out the carpet and they put hardwood flooring in his office, it happens to be very good for his allergies, but these vandals, you know. So this would be a little bit different than that. Yeah. Oh, I was getting to something. Oh yeah. Thank you. So 100 kilograms. 9,800 newtons. Oh yeah. Sorry. Phew. Goodness gracious there. That other one would have been like the strength of 10 men. So there, I mean, if you're really strong, you can push on something with your own weight, maybe a couple times that. So this, it doesn't bode well for Mr. Top Hat there. Unless he's a very heavy Mr. Top Hat. I digress. Let us move on. Let us look at number 6. So I'm trying to hit a good cross-section of these problems. They're all basically one thing, though. They're apply Newton's law to different problems. That's what these all are. All right. There's a common theme here. These are applying Newton's second law to various physical situations. So this one requires a little bit different skill set of thinking. So let's look at it. Number 6. So we've got a 550 Newton physics student. Stands on a bathroom scale in an elevator. Why there's a bathroom scale in the elevator, I don't know. As the elevator starts moving, the scale reads, elevator moves, scale, reading, changes to what? 450 newtons. So then we have a number of questions that were asked here. A, find the acceleration of the elevator. And we're told that take up is positive. All right. B, what's the acceleration? Find the acceleration if the scale reads 670 newtons. And then C, if the scale reads 0, 0 newtons, should the student worry? Explain. Well, if it's like the bathroom scale at my house, no, you shouldn't worry. It just means that you didn't step on it, right? But that's probably not the intent of this question. Oh, obligatory comment. Every so often, there's a WebAssign question there. You're asked to write something down, and it makes some like vague thread about your instructor collecting your work later at some point. That never happens. So the reason I still include those is because often once the key shows, there's a couple of sentences which include precious physical content that you should read and think about, right? But those points are for free, or they're points you can never get. Either way, I wouldn't worry about it, because at some point I will rescale the WebAssign questions in your favor, assuming that there's not somebody out there better than you. So you should find who's doing the most homework and make them do less, pragmatically speaking. But there might be some sleeper in here who's doing more. You never know, right? That's the thing. Did ever guys tell you the story about there was a student in Dr. Skambordis' physics, maybe 2 years ago or something, who complained. He said, some students are getting an unfair advantage on the test. And he's like, what, would they cheat? I mean, what are you talking about? And he's like, yeah, they were working problems at the end of the chapter that you didn't assign, and it's giving them an unfair advantage. And the student was not joking. The existence of that student. I want to kick them out. I'm sorry. But it is, joking aside, that actually is true. I mean, the more you know, the more problems you work, the stronger you are, the harder it is for me to take away your points. Trust me, I don't want your points. I have enough already, especially after the Calculus 2 tests I gave this morning. Some of you, that's especially, maybe it's too soon to make that comment. I don't know. But, all right. We have 4 tests in there. Relax. You'll do better next one. Or maybe you did well. I don't know. Let's see here. So, I digress, obviously. Here's the elevator. Here's the scale, right? So, I'll draw the student as a box of mass M. Let's see here. So, what actually makes the scale reading, right, is the normal force that the scale puts back on the mass, right? What's the force of gravity from the student? It's always mg, right? So, I mean, that's all the forces that are at play here in this situation. It just happens to be in an accelerated elevator, right? I mean, so we always have, what am I supposed to take as positive? Up. So we've got ma is equal to n minus mg, right? And n is also equal to the scale reading. In this case. Right? I mean, how it actually works is there's some kind of like spring inside it, right? And depending on how much the spring gets compressed, you can tell the normal force that's there from Newton's third law. All right, so what's mg? Well, mg we also know. Mg is what? Right? And so there you have it. Although I guess I need to figure out what's m as well because of this. So what's m? 50. See, but that's the thing is, like, I mean, that's the trouble. You can't make up your own units because you got to talk to other people, right? You know? It's like that whole thing with the Hubble telescope, remember? Like we wasted millions and millions of dollars because they used the wrong units. That may be too old a story for you guys. I don't know. Let's see here. I'm sorry, we got to use 9.8 for this. What is it? What's that? 56.12 kilograms. And then, okay. So let's see here. To do part A, what do I got? I've got 56.12 times A is equal to 670 newtons minus 550 newtons. So A is equal to 120 newtons divided by 56.12 meters per second squared. What's the acceleration then? Come on. .14, roughly speaking. As it was forecasted by one of you at the start of this, the elevator is going up, right? That makes sense, right? You've experienced this. I mean, I know it's hard to understand given your experiences with the elevators in this building, but there do exist elevators that make you feel like they're going up when they go up. Such elevators exist. For example, if you have the misfortune of going to the hospital, the local hospital, those elevators, you can tell you're in an elevator, right? They're trying to like illustrate the relativity principle in the elevators here. You know, like this idea that you can't tell if you're in one frame of reference or another when it's not accelerating, you know? Let's see here. What we got? Oh yeah, 56.12a is equal to what's the next one? Oh, I did B. Curses. Oh, 450. Uh-oh. I forget which comment I heard, but it might have been wrong. Well, anyway, I didn't hear. I don't know who said it either, so you're safe with your anonymity. Let's see here, 56.12. So this one's negative, which means what? So get minus 1.78 meters per second squared, roughly speaking. And that was A. And I did A and B out of order. Sorry about that. So in part A, the reading is less than the weight, which means that it's going down, right? In part B, the reading is more than the weight, which means it's going up. In part C, you're free falling. Okay. Which, yes, you should probably be worried about, you know? I mean, I don't know. Maybe you have a death wish. I don't know. Depends on who you are. Maybe you're waiting to collect the insurance money. Maybe it's like your lucky day. I don't know. There's all kinds of things that could happen. Should the student worry? What kind of question is this? I don't know. I should remove this. All right. There's more questions that are essentially the same variety we've already worked. I'm going to go ahead and go to the one kind we haven't really worked one like these ones yet. So number 11 is rather different. You have a car on a flat curve of a highway of radius 230 meters, all right? And I'm just drawing it like a circle for the sake of my artistic convenience. And the car rounds the speed at a curve of 48 meters per second. So I'll draw the car over here. .48 meters per second. This is a flat track. Don't worry, we don't work banked ones in here because I only have a master's in physics and I don't know how to do the one that's sloped. That would have been if I had a PhD. Sorry about that. That was a joke. See here, it's because I don't want to make you guys do it. Sorry, I keep reading problem number 12, which is unhelpful. So the car rounds the curve at a speed of 48 meters per second. What is the minimum coefficient of friction that will prevent sliding? All right.